Good afternoon, everyone. Welcome to my session, Debugging without Debugger. And for all clarity, I'm going to say right away, this is a session that is designed to not teach you anything useful at all. It's just geeking out on investigating the internals of SQL Server without any attempt to be useful. Before I continue with this, I need to put in a word of thanks for the sponsors. Every conference organization always costs money. No conference is ever organized for free. Whether it's an in-person conference or a virtual conference, there are costs involved, there is work involved. The sponsors you see on the screen right now are an important contribution to make conferences like this one happen and possible. So keep them in mind, be grateful that they have contributed to this event. My name is Hugo Kornelis, and I make SQLServerFast.com. SQLServerFast.com is a website that I have set up because I love execution plans. I really enjoy all the information they reveal about why queries are slow, where they can be faster, what's going on, how a query is evaluated and executed. The information in execution plans is insane and awesome and fantastic. However, the documentation for that is terrible. Microsoft does a terrible job of documenting their execution plan stuff. And instead of complaining about it, I decided to just do what Microsoft should have done. So I am building a complete reference for everything related to execution plans. Now, since this is a reference, it's not specifically a tool that is useful for learning things. It's not a quick and simple way to learn about execution plans. So when people told me, Hugo, you should also provide some training material, you should record some of your sessions and put them online, I thought I can do it better. I'm not going to record sessions, I'm going to create custom-built training videos to take you from zero to hero in the area of execution plans. Given the time invested in it, I unfortunately cannot give them all away for free. It's simply too much time involved. I have to ask some money for it. However, since you are here today and since I like all of you, I am going to give you a special offer, a 10% discount valid until the end of May with the code SQLDay21. I believe the code is case sensitive, so keep the upper and lower case in mind. And this 10% discount applies to all purchases until the end of May for the SQL Server Fast Execution Plan video training videos. On the website SQLServerFast.com, I also have other content. I have a blog there, I have some longer articles, and I have resources. And most important here is that you can go to SQLServerFast.com, go to other presentations and then presentation resources. And then you see a list of all my sessions, including the one I'm going to deliver today. You can download the slide deck and the demo code I am using so that you can play with it later, and you can do the same for all my other sessions. So please, I encourage everyone to use the opportunity to review the slide deck later, to play with the demo code, and to come up with your own experiments. Besides having my own website, I do other stuff in the community. I do some work because I have to make a living. None of that is really important. You're not here to learn about me, you're here to learn about what I'm going to teach you about. But the thing that is important is where to reach me. I can imagine that you have questions right now. If you do, please raise your hand and you will be unmuted and you can speak in your microphone or type your questions in the chat. I will try to keep an eye on the chat window and answer them as they come in. However, if you have questions after the session and I'm already gone, you can always mail me or tweet me. I love answering community-related questions about SQL Server and other related stuff. So do use this opportunity if you have any questions. Okay, that was the intro. Now let's dive into the content. We are going to debug the internal operations of a specific operator in execution plans called the window spool. Now, window spool is an operator that, as its main primary function, stores incoming rows in an internal work table so that the same rows can then be returned to the parent operator multiple times. Now, that's not specific to Windows spool. This is basically the description of every spool. Specific for Windows spool is that this operator is doing this in a specific way designed to support windowing functions, also known as the over clause. So if you use an over clause in your query, chances are quite high that you will see a Windows spool in the execution plan. And that Windows spool then helps to get the data correct. So let's jump into a demo, and I'll talk about the prepare steps later, but I'm now going to go into a demo. In this demo, I'll kick it off right away because the query takes quite some time to run. But in this demo, I'm just returning some data from the sales order detail table. Some columns are returned straight out, and then the maximum carrier tracking number for the window of rows that starts 10,000 rows before the current row and ends 3 rows after the current row, based on an ordering by sales order ID and sales order detail ID. So that's what the query does. Let's look at the execution plan to understand how the execution plan works. To the far right, it starts, the data is read from a clustered index scan. This clustered index scan, sorry, that was a wrong click. Clustered index scan reads from the sales order detail table based on the primary key. That primary key happens to be on the combination of columns sales order ID, sales order detail ID. And the ordered property is set to true, which forces the operator to read the rows by index order. So the rows are already ordered by sales order ID and within sales order ID by sales order detail ID. This is important because that's the ordering needed to define the windows. If I had used a different order, there would have been a sort operator in the execution plan. That by itself isn't necessarily bad, but I'm going to peek into TempDB later, and I'm going to try to find hidden objects in TempDB. A sort operator can run out of memory and spool data to TempDB. So then I have multiple things writing in TempDB, which makes it harder to identify things in TempDB that I want to look at, because I might be distracted by things I don't want to look at, but that are there anyway. Because I order by the primary key, and the primary key is then read ordered true by this operator, no sorting is needed, and I avoid that pitfall. Data read from the clustered index scan is then processed by a segment operator. This segment operator marks the start of each segment. Normally, the segment operator would be needed if I had a partition by clause here, some column. I do not have that now. I'm going to remove it so we have the correct query in image. If there is no partition by, then effectively the entire dataset is a single partition. There is not really a need for a segment, except that technically the sequence project operator needs a segment as its child. So we need the segment operator, but because the partition by is empty, we also see that the group by property here is empty. And the entire dataset, all 121,317 rows, are marked as one single segment. So the first row is marked as the first row in the segment, and the rest is all the same segment. Sequence project then does something very simple. It computes an extra column as the row number. That's all it does. Simply add a row number column. Boring. Why does it do that? Well, we'll see that later. But for now, every row gets a number starting at 1, going up by 1 every time a new row is read. And because there's no partitioning, it will be that way for the entire set. Okay, let me go back and quickly go back through the things I mentioned. So we have a clustered index scan to the far right that reads rows that are already ordered in the correct order, so that the windows can be determined without having to resort the data. Then the segment operator places segment boundaries based on the partition by. There is no partition by here, so it's just a single partition. Sequence project computes a row number. and compute scalar then computes two new columns, top row number and bottom row number, that are the 10,000 preceding and the 3 following that we want to see in each window. After that, we have another segment operator that is again there for technical reasons. It once more marks the entire dataset as a single segment. And then we have window spool, and window spool returns this entire window of rows for each row, or rather, technically, for each row from sales order detail, it returns first that row itself, then the 10,000 preceding row, the current row, and the 3 following. So it's the total of 10,005 rows for each row. And that's why the number of rows returned by window spool is so high. The window spool does this based on a window count. That is, one row is added by window spool, and stream aggregate then groups by that window count to get the rows back again. And in the defined values, it will compute the maximum of the carrier tracking number and use the any to just get the first data, the row from the first data for all the other columns. That's how all this works. Now let's return to the demo, to the slide deck, and move on to what we actually want to talk about today. How exactly is this work table stored? The parts of that is documented. If you go to the internet and you look at the documentation, you will find that if the number of rows can impossibly ever exceed 10,000, then the work table will be stored in memory. However, if there is a theoretical chance that the number of rows is more than 10,000, and this is determined based on what is in the window specification in your query, not on what is in your data, because that can change, then it goes to disk. So that's the reason why I used 10,000 preceding and 3 following in my query. I wanted to be above that 10,000 threshold because I want to investigate the on-disk version for this session. Now, investigating something on disk is hard because there are some problems we have to overcome. It's all temporary structures. It's internal. I cannot tell SQL Server, hey, just keep that item there for a bit longer, because once the query is done, SQL Server says, I don't need it anymore. I'm going to release the pages and I'm done. So I need to give myself the time to investigate the structures, even though the query duration is limited. And yes, the query in the demo took very long, 40 minutes. Normally it's 6 minutes. So I'm just putting quite a strain on my laptop. It's using a lot of resources. But the query duration is limited. And I can make queries slower, but how slow is slow enough? If I slow the query down so that it runs for 6 hours, is that enough time? Or am I nearly there after 6 minutes, almost found it, and then the query stops and I have to restart? So one thing I can do is use the debugger and halt the SQL Server process. Problem there is the debugger is insanely complex. I don't understand it. I'm not smart enough for that tool. Also, when the debugger halts the process, I cannot use SQL Server tools. So if I want to investigate a page in TempDB, I do not even know whether it's already flushed to disk or in memory only. I don't know where in memory to find it. I have a lot of hard issues to resolve. Whereas if SQL Server is running, I can simply type dbcc page. It's not an officially documented statement. It's well known enough that you know how to use it. And I can use dbcc page, and you will be able to find the data there. And the SQL Server will figure out whether the data is in the cache or on disk and will give me the correct data. So I don't like using the debugger. Like I mentioned, I could create a very slow query, but how slow is slow enough? What if it's just done before I have my information? The next time I run the query, because it's temporary internal objects, they can be stored somewhere else, and I have to do everything over again. So what I did instead, I just used documented stuff. I use logging and blocking. SQL Server is concurrent, it supports concurrency. I should be able to have multiple sessions not get in their way, and I'm going to abuse that to block a query as long as needed. And I call that freezing a query. So what I do is, and I have it as a comment here, but I need the results. So I need to run the query first. Luckily, I have already done that. I have the query results here. So I don't need to run it again. It's there already. Then I have this block of code. I'm going to copy that in a new window. And what I do here in this window, I create a table, and I call it block window spool because I use it to block the window spool. And the table definition matches the exact columns that are output from the query. So the same 4 columns with the same data types. The nullability is also, I use the definitions I know from the AdventureWorks sample database, plus the logic in the query to determine that these 2 are not null. These 2 are not relevant. I don't need them, so I just leave them null. And I also look at AdventureWorks and I know that the combination of sales order ID, sales order detail ID has to be unique based on how the input table of the query is defined and what the query itself does with it. Then I'm going to start a transaction and then insert a row there with these 2 values. These 2 values come from the results I have here. So I'll scroll down a bit, not that far, always a bit fickly, find the exact place. So it's this row that I decided, and I chose this row because here we are past the part where we have a full window. I wanted to make sure that I already have a full window of 10,000 rows, because now I can also see whether the first 100 rows that are technically no longer needed are still in the temporary table or are removed again. So I use these 2 values and I put them here. And because there's a primary key on these columns, this will create a lock in that primary key. As you see, I do not commit or roll back the transaction. That's commented out. I'm not executing this, so we now have an active transaction. And now I have the same query here. And I need to make sure that the execution plan is the same. I had some tests where I used other code at first, where the, I put the wrong thing, my bad, I should have clicked that one. Let's try that again. I had some tests at first where after adding the insert statement, the shape of the execution plan changed because SQL Server optimized for inserting. I don't want the shape to change. I want to be sure that the data is inserted in exactly the same order as I got this when I first ran the query. Because now I know that after processing these 10,099 rows, SQL Server will try to process this row, and that will fail because it is blocked. And as you see, the numbers and the execution plan stop changing. There is no change anymore. Everything is blocked. This is also why in the prepare I set the maximum degree of parallelism to 1. If I had allowed SQL Server to go parallel here, other sessions would still be writing and the query would eventually finish, except for that 1 row. And I just want everything on a single thread. Just I have now a full control. I know exactly what data has already been processed and what not. And I can leave this block as long as I want. If I need 7 hours to investigate, I'll just wait for 7 hours, investigate, and only when I'm done with my investigation, I can roll back this transaction, and now the log is gone, and this query runs again. It doesn't need to finish this time, so I'm going to stop it. But now I have my problem solved. I can pause the query, can freeze the query as long as I need to get my investigation done. So the next step is we need to find the objects I want to look at. Windows Spool stores data on disk in TempDB in an object. I need to find it. So how? Well, just type select star from tempdb.dbo. or tempdb.sys. Oh yeah, we need an object name. Well, that's why I ran this with statistics IO on. So I can see that we wrote to a table called work table. Except it isn't called work table. It is a work table. Statistics IO doesn't provide a name. Work table is a token name. Tell me I used a work table. Isn't named this. If I use select star from work table in TempDB, I will get an error because there is no object named work table. So that doesn't work. The next thing I tried was looking in DMVs, such as sys.indexes or sys.sys indexes. The best way to do that is to simply have them twice and then compare the results of the two queries. So let's look at this. I query sys indexes and sys.sys indexes. Now, copy the code into a new window and I do the same thing here. So I run the queries here, I run the queries here. Obviously the results are the same because I did nothing in between. Now I'm going to create this block window spool table again, and I'm going to start this query again. And at this point, window spool is writing rows to a temporary object. So now, when I refresh one of these two windows and do not refresh the other, I should see a difference. And I planned to Control Tab in between the two, but the first thing I did was, this is the window before I started the window spool. The total number of rows is visible here, 380. This is the window after I started the window spool. Now there is this extra object created. I still have 380 rows. So nothing changed in the result set. And I can compare the two by Control Tabbing in between the two windows. I will not see a difference. There is no difference because this work table is not stored in the system tables. There is a reason for that. The work table is only used internally by Windows Spool. System tables are there so that other connections have information about the objects. Other information shouldn't ever mess with this object, so there is no reason to store it. And then, now, if it's not stored in the underlying in those DMVs, perhaps it is stored in the actual underlying system tables and just hidden in the DMVs. So to check this, what I did was I repeated this experiment with the execution plan enabled. Because if you do a select star from sys.indexes, what actually runs is this execution plan that runs a lot of stuff and gets its data from various physical system tables that you cannot access directly. Like, for instance, the sys.idx stats where everything is stored. And this table, as you can see here, has 214 rows, of which 166 are red because of this predicate. See, some stuff is hidden. Not everything that is in sys.idx stats is actually exposed to us. So perhaps that's the clue. Yeah, well, except that before we started the query, we also had 214 rows red, of which 166 were returned. So again, there is no difference. And I actually did use the DBCC page to check the pages of sys.idx stats to double check. There's really nothing stored for the work table in all of those tables. So that was a bummer. And I could not find how to access the data that is used by the Windows spool. And then I realized I am already abusing the fact that SQL Server is a multi-user system, that concurrency is supported. That same fact can be abused again, because even though nobody else should care about the work table used by Windows Spool should still care about protecting that data. We want to make sure that no other connections are using the same storage area in TempDB. So the PFS page, that's the page free space page, determines which pages are used and which pages are free for use. If TempDB allocates space and does not mark them as used in the PFS page, other connections might start using those same pages and you will get errors. So I'm pretty sure that the PFS page will have artifacts of all the objects allocated by the Windows spool, even though nobody else sees them. And once I have that, I can look at an allocated page, find the allocation unit, and then you use a DMO called DMOS buffer descriptors to find the rest of the pages. Or alternatively, use the previous and next page pointers, or check all the pages that were not allocated first and were allocated later. Then I can inspect those pages. So let's look how that works in the demo. First close some windows I don't need anymore. Let's stop this and start all over. But before I start all over, I'm also going to restart the instance. The reason I do that is because I found when I tried this that at one point the SQL Server TempDB starts to have some pages allocated. It doesn't need them anymore. It keeps them allocated for a bit, and that's probably not unlimited. The TempDB knows it's very volatile. It needs to get some data, store it, release it again, store it again, release it again. So it keeps a pool of pages allocated even though they are not used, and doesn't give them back every time. So now I am on a fresh system. TempDB has nothing allocated yet. It's easier to see the differences. So I'm basically using the same trick again. I'm copying some paste to a new window. And if I execute that page here to check the PFS page and execute the same code in the second window, we will of course get the exact same data in both windows. But that changes when I set up the freeze and run the windows pool. And now I'm going to wait for a bit because at this time stuff is moving in TempDB. The windows pool is writing there, is reading, stuff is in session, and I don't want everything to be moving while I'm looking at it. I like to look at stuff when it's at rest. So I am going to wait until we hit this blocked row number 10,100, and at that point I will start my investigation. Cool. I can see by the numbers in the live execution plan that everything is now paused. Everyone is waiting until I release this blocking row, and I'm not going to release it. Now, this is the window where I have my before data. I'm not going to refresh this. This is the data on the PFS page before the Windows pool started. I am going to refresh this window, and this is the data in the PFS page after we restarted. So now I'm going to Control-Tab in between the two. This might look a bit flashy on your screen, but I'm going to page down and Control-Tab again. And now you see that there are some status bits that are different. Those are not very interesting. Let's just keep scrolling. In some of my runs there have been cases where rows have ghosts or have no ghosts, and that's a fake difference that I need to ignore. I need to look for pages that were not allocated before and are allocated now. And here we see a difference. So before I started the query, page 126 and 127 were both not allocated, so they were free. Then I started the Windows pool, and now 127 is still not allocated, but 126 is allocated together with 125. 425 was allocated, but 126 not. So the change is page 126 that went from not allocated to allocated. I'm going to fill that page number here, and I'm going to inspect the data on that page. And at this point, I'm only interested in the header. In the header, I see an object ID that is negative. That is confirmation for me that this is not a normal object. Negative objects IDs are always used when there is a temporary object that is not a normal object. And this is a number that I cannot use because it's only stored internally and not in DMOs. The allocation unit is a number I can still use in some queries. Like for instance, this query. So I'm pasting in the allocation unit. And now I'm going to execute this to find all the pages that are allocated to the same allocation unit. See an index page, an IAM page, and multiple data pages. Lots of data pages. I also ran this query once after pausing the Windows pool when it had 100,000 rows. That would have taken multiple minutes. I'm not going to do that in a demo. But I did that to make sure, and at that point I had multiple level of index pages. So I had already a good confirmation that this looks like a B tree. I also see that the index page is page 369. So let's copy that page number and check DBCC page to find its contents. Now, DBCC page is a bit hard to read. With dump style 3, that you could put here, you get better information, but that doesn't work for internal objects. So I have to use dump style 1 and then decode the information myself, and that's hard. However, based on information I got from the books from Caleb Delaney, I know that these 4 bytes are a file number and these 8 bytes are a page number. So in file number 1, well, there is only one file in TempDB because in the prepare, I have made sure that, well, it's in comment, I set it up, I have set up my instance to have just a single TempDB file. That's not good practice for performance, but it helps me find the data because everything is in file 1. That makes it easier. But now it's page number hexadecimal 0170. You need to read this byte reverse. So it's 00000170. And I can use a hex calculator to figure out what the decimal version of that is. And let me just bring up my calculator. Hexadecimal 170 is decimal 368. So now I'm putting in page number 368. And if I look at that page, I will see that this looks like a data page. And what makes me very excited is this information I see here, 4911-403C98. Why do I get this excited for this weird information? Because in the results of my query, if I go back to the first row, that is one of the carrier tracking numbers, 4911-403C-98. 4911-403C-98. This is the first row from our data set. We have found the data that the Windows spool stores in an internal hidden object that we are not supposed to see, but we saw it anyway. So that fixes the problem of finding the objects. Now I still need to figure out the structure, because I want to know how Windows spool stores. Not only where, I want to know how Windows spool stores this. So let's first check what we expect. I looked at the fragment of the execution plan, and I did that in the execution plan, but I put it on the slide now. And I looked for the segment operator at what columns are returned. The columns returned here are the columns that are passed into the Windows spool. I also checked the Windows spool to see which columns it returns to its parent, the stream aggregate. And I see that there's a lot of overlap there. So the overlapping columns, it's very likely that the data in these 4 columns and in the segment 1009 column is all stored in the work table that the Windows spool uses. There's also a top row number and a bottom row number, and based on how Windows spool works, I actually expect those in the Windows spool as well. The window count 1010 is produced by Windows spool as it returns rows, and I don't see any reason why that would be in the work table. So my expectation is that the 7 columns returned from the segment operator to Windows spool are there and nothing else. But I could be wrong. But I go into the exploration with that expectation. Then, as I already mentioned, I used the book from Caleb Delaney to help me figure out DBCC page information. So here is a screenshot I took from an earlier exploration when data was on slightly different pages. So the data is not the same because this is the index page. And if you decode the index page, the first byte is the index row. It is the status byte, and 06 means it is an index row and there's no null bitmap here. Like I already mentioned, we have the page pointer and the file pointer and the page pointer, which point to the first page on the next level. And then we have 8 bytes of garbage. The reason that there's garbage here is that this is the first entry on a level in a B-tree index. In a B-tree index, the first entry on the first page of any level is garbage because it's never used. So we don't need to look at this. The 8 bytes are still there because it is defined as using an integer, or a big integer, sorry, so it has 8 bytes, but they're not initialized. Whatever happens to be there when SQL Server allocated the page is not overwritten. Second index record also is an index row, but this time the status bytes say, hey, we do have a null bitmap now. We have a pointer to another page number 282 in file 1. And here, these 8 bytes are actually an index key. So the first entry on page 282 is for the index value 113. And because we have a null bitmap, we have 2 bytes with the number of columns, 1 column. We just saw the data there, and there are no null values. But We already knew that because we saw the value. For the third index row, we get something similar. And you can look at all the index rows and you will see similar stuff all the time. So this looks like a normal B-tree root page. Let's look at the data pages. And the first data page, here's a screenshot of a start of the first data page, and that's the one we just saw on the screen as well. In a data page, the first 2 bytes are the status bytes. And 3000 means it's a data row. There is a null bitmap, and there is at least one variable length column. Then we have 2 bytes that tell us where the fixed length data ends. So everything after these 2 bytes until position hexadecimal 205 is the fixed length data. We'll go into the details of the data later, but first we'll move to that position 205, and there's 2 bytes there, and that's the number of columns. So we have 8 columns stored in total. After that comes the null bitmap. Because the number of columns is 8, the null bitmap is 1 byte. For 1 to 8 columns, the null bitmap is 1 byte. For 9 to 16 columns, the null bitmap would have been 2 bytes, and so on. In this case, it's 1 byte. And after the null bitmap comes 2 bytes with the number of variable length columns. So we have 2 variable length columns in this row. And the first variable length column ends just before position hexadecimal 2e. And the second ends just before hexadecimal position 46. So where exactly does this first length column end? Well, just before that 34. So the first variable length column has 0 length in this row. That makes it hard to understand what's there because it has no data. So it's a bit hard to backtrack. Second variable length column ends, of course, just before the end of this entire record. And the data there, we already recognized it. We got all excited when we recognized it as a carrier tracking number. So this is the variable length column storing the carrier tracking number. 2 bytes per character because it's n varchar. Then we go to the fixed length data. It starts with, if you read it again in reverse order, 00000001. So it's just 8 bytes with the number 1. That's the row number. We expect the first row to have row number 1. We expect the row number to be stored, and here we have a row number 1. Cool. After that, I did a bit of cheating. Instead of trying to decode the hexadecimal information, what I actually did was I went back to the original data and I said, I expect this number, 43659. So let's enter that in the decimal set. Copy. Let's enter that here. And then hexadecimal AA8B. So that's what I expect. Okay, well, then it's easy to find because SQL Server reverses the bytes, and this is AA8B with some zeros before it. So here we find the sales order ID, an integer, 4 bytes. The next 4 bytes are also an integers, the sales order detail ID. I also expected that number. And then I looked at what came after that, and it was 05F1D8, and it made no sense at all. So I scratched my head a bit, and then I decided, you know, I'm going to start at the end of the fixed length data. I know where the fixed length data ends. I know there's 8 columns total. I know there's 2 variable length columns, so I have 6 fixed length data columns. And the last one ends here. That's a lot of zeros, and then 4. Well, that makes sense. That's the bottom row number. And now that I know that the bottom row number are these 8 bytes, and I see just before that a whole bunch of Fs, well, for the first row, top row number is a negative number. Row number minus 10,000. That's minus 9999. In hexadecimal, that's FFFFFD8F1. And now I suddenly understood why 05F1D8 made no sense, because that's actually 2 fields combined. I should have looked at 05 only. So I have only 1 fixed length column field left, and that's this 05 on the first row and FE on the second row. And I still don't know what that is. So I have already identified 6 columns. I have 1 zero length variable length column left and 1 single byte left. Let's look at the single byte first. Now, when I was investigating, I had to restart a few times. And sometimes when I restarted, I noticed that the data changed. On an index page, that makes sense because indexes point to data pages. Those data pages can be allocated somewhere else, so the pointers have different values. On a data page, I do not expect data to change because the same data is stored every time. And yet it changed. And as I scrolled through the rows, I noticed something else. That is that the first row in the work table always had an odd number in this byte, and all other rows always had an even number. And that's when I realized I am looking at it wrong. I am looking at a byte, but a byte is 8 bits. And this byte uses 1 bit to store segment 1009, and the other 7 bits are unused. And unused data is not initialized in SQL Server. If it isn't used, it just leaves there whatever garbage was there when it started allocating the space. That's why between runs, sometimes the data changed there because they were unused bits, and they can change. The used bit, that is the bit that determines odd or even, that is always the same in between runs. And segment 1009 is indeed 1 on the first row and 0 on all other rows. So there we have the solution for this fourth fixed length column. It uses a byte, but it stores only 1 bit, segment 1009, and it has 7 unused bits. And then we only had this variable length column left. And no matter which row I looked at, no matter how often I repeat the executions, they were always 0 length. In all 120,000 rows, in all pages, in all runs, they were always 0 length, and nothing changed that. So I had no data to look at to understand what it was, and I don't think I would have figured it out if I had not already in the past done the same exercise for other spool operators like table spool and index spool. But I had already done this before for table spool and for index spool. So that gave me a background, because for the table spool and the index spool, I figured out that the work table always uses a non-unique clustered index. A non-unique clustered index adds a unifier column that can be used to distinguish the rows that have the same data. If there is only one row with a certain value, then the unifier column is left empty. It's 0 bytes. Otherwise, it's 8 bytes. 4 bytes, I'm sorry. In this case, what I figured out was there is apparently a clustered index on the row number. The row number is guaranteed unique, but SQL Server, for whatever reason, still declares this work table as a clustered index non-unique on this row number. Because it's declared as non-unique, SQL Server adds this extra column for the unifier, but leaves it 0 length if it's not needed. And because the actual data is in reality unique, it is never needed, and it will never be anything other than this 0 length variable length column. But that's why it's there. And that solved the last problem I had to overcome, reading and interpreting the data. I finished that. I now know how the data is stored. So let's recapture. What did I discover during this journey? I discovered that if a Windows spool stores data on disk, it uses a work table that is declared using a clustered index. This clustered index is indexed on a column that is determined elsewhere in the execution plan using the row number function. It's simply an ascending number for each row increasing by 1. And even though this is guaranteed to be unique, it's impossible to ever have duplicates there unless the execution plan does really weird things and is completely bugged. Even though this data will never have duplicates, it's still declared as non-unique. And because it's declared as such, there is room for a unifier column in the rows, but it's never used. And as I expected, I got that confirmed. All of the columns that are passed into the Windows spool are stored in the work table. Extra column that is returned by the Windows spool, but it's not in its input, is not stored in the work table. And that concludes everything. I know I had to rush a bit because of the restart I had to do and because of the frozen screen. But like I mentioned before, I am planning to do a complete re-recording of this session later and then put that online. So keep an eye on my blog if you feel that you missed too much and you want to see it again. For now, I'm going to ask all of you, if you have a question, raise your hand or type it in the chat. And while you do that, I will also tell you that if you have questions later, mail me, tweet me. Don't forget to thank the sponsors. Yeah, over to you. We still have a few minutes left. So what are your questions? Question from Mariusz Navruklen. I hope I pronounced it correct. How big is the temp table compared to the results table? So if you look at the execution plan I showed, all of the rows returned from the segment column to the window spool gets stored. So normally if they are partitioning, then the temp table will reset on a partition. So if I used partitioning here, if I had done that by something, then whenever a new partition starts, the temporary table is emptied and it starts again. So then the amount of rows in the temporary table is limited by the size of the partition. Without that partition column, I cannot type anymore. Without that partition column, the entire result set is a single partition, and that single partition gets stored entirely. So all 121,317 rows will be stored in the temporary table as it processes its last row, and then it releases. So that's the final biggest size you get, is 121,317 rows for this demo, the entire input. If there had been a partition by, then it would have been the size of the largest partition. Okay, if there are no questions left, then I'm going to give you back 4 minutes of your time, and then you can beat the queue for the restaurant, which obviously in a virtual conference doesn't mean anything, but it's still great. Thank you all for your attention. Again, please accept my apologies for the technical difficulties there were. I will put on a recording of this online, but I have to make it first, so that will take some time. Enjoy the rest of your stay here at SQLDay, and thanks to the organization for having me. Bye-bye.